In this video, we'll get a little bit of practice working with Taylor series. In the box, you see the first series there is a Taylor series, the general form, if you will, of a Taylor series, and then below that, a Taylor series when it's centered at 0 is called a Maclaurin series, and that's what we're going to be starting with example 1. Find the Maclaurin series for f of x equals 1 plus x all to the negative 3 power and its radius of convergence. So first, notice that in order to do a Taylor series, we need repeated derivatives, right? So we'll have the function evaluated at a. In this case, it'll be at 0 because it's a Maclaurin. And then the first derivative, the second derivative, the third derivative, and so on and so forth. Our goal is going to be to find a pattern that will allow us to write up this series. So we'll start off with f of x, which is 1 plus x to the negative 3 power. And then we're going to take repeated derivatives. So f prime of x will equal negative 3, 1 plus x to the negative 4 power. And then we'll continue like this. Now, because we're dealing with a Maclaurin series, we'll go ahead and evaluate each of these at 0. Now we'll use these values here to build our Maclaurin series. So this will give us 1 minus 3x plus 12 over 2 factorial, which is 2, x squared, minus 60 over 3 factorial, which is 6, x to the third, plus 360 over 24, which is 4 factorial, x to the fourth, and so on. Now our goal is to come up with a pattern that's going to allow us to rewrite the function as a power series using summation notation. With this particular problem, the pattern is a little bit hard to see. Let's take a look at each term when we have a denominator of 2. The pattern still might not be obvious, so I'm going to rewrite this yet again like this. So now we're seeing a 2 in each denominator. We're seeing alternating signs starting with positive, and we're also seeing that each term's numerator is the product of 2 consecutive whole numbers. So if we start our summation at 0, first let's get the alternating sign. In the numerator, we notice that we need to multiply 2 times 1 for the very first term. So that's going to be n plus 2, n plus 1. When n is 0, we're going to get 2 times 1. When n is 1, we're going to get 3 times 2. When n is 2, we're going to get 4 times 3, and so on and so forth. And then on the bottom, we've got our 2 and x to the n. That is the Maclaurin series representation of the function 1 plus x quantity to the negative 3 power. Next, let's find the radius of convergence using the ratio test. Simplifying this down, we get the limit as n approaches infinity of n plus 3 over n plus 2 absolute x. Taking that limit, we simply get absolute x, and that needs to be less than 1 in order for our series to converge. So therefore, our radius of convergence is r equals 1. Example 2, find the Taylor series for f of x equals 1 over x centered at a equals 1. So once again, we're going to go ahead and take repeated derivatives, starting with our function f of x. And that will look something like this. Now we evaluate each one of these at a equals 1. And now we're ready to write the Taylor series for this function. So we have f of 1 is 1. We have f prime of 1 is negative 1. The second derivative of f at 1 is going to be 2. Then we get minus 6 over 3 factorial. And then 24 over 4 factorial. From there, we can notice that our first term has a 0 factorial under it, and the second term has a 1 factorial. And so now we notice that our numerators all have n factorials, as do our denominators. So we're going to get the sum, n equals 0 to infinity, negative 1 to the n, that'll give us our alternating signs, and we have n factorial in the numerator, n factorial in the denominator, x minus 1 to the n. Of course, we can simplify that like this. And there's our Taylor series representation of f of x equals 1 over x, centered at a equals 1. Example 3, find the Maclaurin series for f of x equals cosine pi x. Now, if you already have the Maclaurin series memorized for cosine x, you can just plug in the pi x into that power series and you'll have it. But we're just going to go ahead from scratch and start off by taking our function and repeated derivatives, just as we did in the previous two examples. Now, since we're constructing a Maclaurin series, we will evaluate each of these at 0. So the Maclaurin series for our function f of x equals cosine pi x will equal f of 0 plus f prime of 0 x plus f double prime at 0 over 2 factorial x squared, f triple prime at 0 over 3 factorial x to the third, like this. That will give us 1 plus 0 plus negative pi squared over 2 factorial x squared plus 0 again plus pi to the fourth, 4 factorial in the bottom, x to the fourth, like that. Here we notice that we only have even indexed terms. So again, we're going to have alternating signs. So we'll have negative 1 to the n. In the numerator, we have pi to an even number. So we put 2n there. In the denominator, we have a factorial of an even number. So 2n factorial. And we have exponents on x also even. You can go ahead and start plugging in n equals 0, n equals 1, n equals 2, and you'll find that you're getting these first three terms. There is our Maclaurin series for f of x equals cosine of pi x. Notice that if we had known already that cosine x is the sum n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial, then we could have simply written that cosine of pi x is equal to the same series, except for we would be replacing our x here with pi x, like this. Let's go on to the next one. Example 4, evaluate the indefinite integral, the integral of sine x over x dx as a power series. We could start off by generating the Maclaurin series for sine x just as we did in the previous problem for cosine x. But for this, let's go ahead and assume that we've already found that. The Maclaurin series for sine x is the sum, n equals 0 to infinity, of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This implies that sine x over x should equal 1 over x times our power series for sine x. Now, if we multiply in this 1 over x, it's going to look like this. Now we can cancel the x in the denominator with an x on top. And there is our power series representation of sine x over x. So we can now integrate sine x over x dx as a power series. We're integrating with respect to x, so our negative 1 to the n will remain the same. We're going to add 1 to the exponent. In the denominator, we're going to need that 2n plus 1. And of course, we still have the 2n plus 1 factorial plus c. And there we have our power series representation of the integral of sine x over x dx. Example 5, use the fact that tan inverse of x is equal to the sum n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over 2n plus 1 to evaluate the limit as x approaches 0 of x minus tan inverse x all over x to the third. So first, we're just going to go ahead and replace our tan inverse x in this limit with our power series. Now we'll go ahead and list out our first several terms of this power series. When we plug in 0, we're going to get a positive. We're going to have x to the first power and a 1 in the denominator, so we just get an x. When we plug in 1, we'll have a negative. We'll have x to the third and a 1 over 3. When we plug in 2, we'll have a positive. We'll have 1 over 5 x to the fifth. And then from there, we'll get a negative 1 over 7 x to the seventh plus, and that's just going to continue like that. Now, if we go ahead and distribute the negative, we get something like this. Our first two terms will cancel. And now we can divide every term by x to the third to get 1/3 minus 1/5 x squared plus 1/7 x to the fourth, like that. Now if we take the limit as x approaches 0, we notice that every term after 1/3 will zero out, and just like that, we found our limit. Example 6, use the fact that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial to find the Maclaurin series for f of x equals e to the x plus 2e to the negative x. So since we have that e to the x is equal to this power series, that implies that e to the negative x is going to be exactly the same, except we're going to replace negative x for x in the numerator like that, which can be rewritten this way. Now, if we take our function f of x equals e to the x plus 2e to the negative x, that's going to equal our power series for e to the x plus 2 times our power series for e to the negative x. Combining these, we get a power series that looks like this. If we factor out the x to the n, we get this. And there is our power series for the function e to the x plus 2e to the negative x. Go ahead and do the rest of the worksheet on your own.